Welcome to Network Analysis ELE 311T. This is the first lecture of this course. To understand networks and to analyze them, we need certain tools that we have already studied. And the most important of them is the tool of mathematics, which is the differential equations. We have already seen in a basic electrical engineering course that we studied in the first semester that network elements like inductance, capacitance are governed by differential equations. Their governing equations are differential equations. For example, in case of the inductance, we can write the voltage drop across the inductance and relate it to the current flowing through the inductance through the differential equation, which is given by Vt is equal to L dit by dt. Similarly, for the capacitance, we can relate the voltage across the capacitance and the current through the capacitance by the famous relationship, which is given by It is equal to C dVt by dt. So all these circuit elements, when they're put in together in the form of a circuit, the governing equation that you'll get would be a differential equation. Like, for example, if you have a simple DC circuit in which you have a voltage source, you have an inductance, say, and then you have a resistance, and then there's a current that's flowing through the source, through the circuit, we can straight away write that Vt and that the voltage applied is equal to L di by dt plus Ri. So this is nothing but a differential equation, right? And to be very precise, it is an ordinary differential equation. So we have to be familiar with the ways to solve ordinary differential equations in order to solve and in order to analyze circuits. This is something that we have already done in the first semester, but still a brief review of how to solve ordinary differential equations and their application in circuits. That's the objective of the first lecture. So let's start. Now I'll basically write down first the equations for the network elements, and then we'll start by talking about differential equations. So what are the elements that are part of the network? You have sources in a network, and you have loads in a network, right? And the word network and circuit is used interchangeably, although there is a small difference between them. Circuit is a network which has all elements in enclosed paths, right? Which has all elements within a closed path, right? So, and a network may have some open part also. Like for example, this is a circuit because all the elements, the three resistances, are lying within a closed path. You can draw a closed path and all three of them will fit in. But if for example a resistance exists here, it is still a network, but it no longer remains a circuit. So this is a slight difference between the two. So I was talking about what are the various elements in a network or a circuit. So normally you'll have sources, you'll have loads, and in sources we'll have voltage sources, we may have current sources. This is what you have already seen before, and then there are differences, further differences. The sources may be ideal, they may be non-ideal, they may be independent, they may be dependent, they may be constant in the sense that they may be DC, or they may not be constant, that they might be AC sources or variable sources. So this is something that we have already learned. And loads generally are of three types. These are idealized loads. You have a resistance, you have an inductance, you have a capacitance. These are the governing equations that you have studied are ideal for idealized loads, in the sense that there is no resistance which does not have a capacitance or an inductance, but we talk about them separately as if the resistance exists entirely alone, the inductance exists entirely alone, and the capacitance exists entirely alone, which is not really possible in the practical world, because inductance, for example, is made of wire, and every wire has some kind of resistance also. So actually any inductor that you'll see will have some resistance of its own, but we talk about ideal elements. So you have a resistance, you have an inductance, you have a capacitance. This is our sign convention. We say that the current, if the current is drawn like this and it flows from the plus end of the voltage to the minus end of the voltage, then the governing equation for the resistance is Vt is equal to RIT. In a similar way, for the inductance, if you draw the current like this, which flows from the plus end of the inductance of the voltage to the minus end of the voltage, then you see that Vt is equal to L dit by dt. And similarly for the capacitance, this is your current and the voltage, the sign convention. This is called the passive sign convention. This is again the voltage across the capacitance, and you say that the current to the capacitance is given by C dVt by dt. So this form is the differential form of the equation, differential form of the governing equation. This may not necessarily be the only form. You can also write the integral form of the governing equations. This is an algebraic equation and it remains the same. It does not change because there is no differential part. So you can write the integral form of the governing equation also. Like for example, for the inductor, this equation that you have written here, this one, can be written as an integral equation. You can write by taking dt on the left hand side, dividing by L, and then integrating, you can write it is equal to 1 by L integral Vt dt. And this integration is actually from minus infinity to t. What does it mean? It means that the current at any time t in the inductor is the result of the integration of all the voltages that have been applied from minus infinity to t, to the point t. And then you also assume in this case that the current at minus infinity is 0. So you start from a point minus infinity and you apply voltages, different kinds of voltages on the inductor, different waveforms maybe, and then you integrate all of them up to point t. You get current at time t. So this is a kind of memory element, in the sense that it stores all the information and integrates it to give you the current, all the information of the voltage applied. So there's a kind of memory in it. The current at any time t does not depend only on the voltage at time t. It depends on all the voltages that have been applied in the past up to the time t. Compare it with the equation of the resistance, for example. The resistance is going to be it is equal to Vt by R. So for the resistance, the current at time t is just the voltage applied at time t divided by the resistance and resistance. Please remember, in these cases we are taking the inductance to be constant. It does not vary with time. The resistance is constant, does not vary with time. That's why we are able to take it out of the integral. So this is the integral form of the equation. You can break it further if you want into, you can integrate, you can break the integral. You can say that the current at time t is going to be 1 by L minus infinity to t, say for example t1 Vt dt. We are breaking it at t1 plus t1 to t Vt dt. Again, this is your choice. You are breaking the integral at some point t1. There's nothing wrong in it. This can be done mathematically. So if you look at the first part, this part, you see that by comparing this part and this equation that I've written earlier, you see that this is actually the current at time t1, because you're integrating all the voltages from minus infinity to t1 and dividing by L. So you can write it is it1 plus t1 to t Vt dt 1 by L, right? So the current at time t is the current that was flowing at time t1 plus all the voltages integrated from t1 to t. And then you have seen another form of this equation when t1 is equal to 0. So at that time, when t1 is 0, you have written t1 is 0. For t1 is equal to 0, you have written it is equal to I0 plus 1 by L 0 to t Vt dt. So this is another way of writing the same thing. Similarly, we can write for the capacitor these equations in the integral form. So for the capacitor, the differential equation we have already seen. The differential equation of the capacitor is IT is equal to C dVt by dt. You can write this in the integral form by again taking this dt on the left hand side, dividing by C, and then integrating on both the sides. We'll get Vt. Is equal to 1 by C minus infinity to T IT dt. Again, herein you're assuming that the voltage at minus infinity was 0. Then you started applying currents to the capacitor, and the voltage at any time t, Vt, is the integration of all the currents that have been applied from minus infinity integrated up to t. So again, this is a kind of memory element in the sense that the voltage at any time t is dependent on everything that has occurred up to time t in terms of current, right? So what we did with the inductor, we can do with the capacitor. We can break this integral. We can write Vt is equal to 1 by C. Then you can break this up from minus infinity to T1 IT dt, plus then again from T1 to T IT dt again, and then you can write Vt. If you see this equation, the first part of this equation, and you see this equation, compare the two, you'll see that you can write the first part of this equation as Vt1, because this is integrating all the currents up to T1, wherein you have defined the voltage as integrating all the currents up to time t. Vt is integral minus infinity to t. So this is the voltage at T1. So you can write this as Vt1 plus integral 1 by C T1 to T IT dt. And then you can always say that T1 is 0, and you'll write this equation which you have seen before. T1 can be 0, so you can write Vt is equal to V0 plus 1 by C 0 to T IT dt. So these are the different forms of the differential equation, the integral form of the governing equations for the network elements, inductor and the capacitor. So these forms we'll be using again and again. We have to be very good at using them. It's basically how the initial conditions are important in determining the voltages and currents at any particular time t. So next we are going to see how differential equations are used, and the knowledge of differential equations that we have is used to solve problems related to network analysis. So what are the differential equations that we're going to talk about, and which differential equations are going to be useful, which methods are going to be useful in a study of networks? That's what we are going to see next.